Good evening, students. I'll start with the class. The previous class, we started with a new chapter, that is thermal properties of matter. If you had not watched this, attended the previous class, please make sure you watch the recording, because if you miss one class, then whatever happens in the second class becomes difficult to understand. So we had seen there's something called as thermal expansion. It's nothing but whenever any object is heated, means there's some heat given to any object, there are chances that the object may expand. Okay, whenever any object is heated, so this is expansion of any object due to heat. So we had three types. One was linear expansion, one was area expansion, and the third one was volume expansion. This was like this. Suppose this is your original rod, so length increases in case of linear. In case of area, the area increases, expands, and in case of volume, then this increases, outer area, volume increase. So this is linear expansion, this is area expansion, this is volume expansion. And we had seen the change, whatever is this, this is delta L, change in length. Okay, this much it is increasing. Same way, this is change in the area, delta A. This is change in the volume, delta V. So delta L upon L is always proportional to the change in the temperature. The more you increase the temperature, the more this length will increase. So it is directly dependent on the change in the temperature. So whenever we remove the proportionality sign, we had put a constant instead of K, we used alpha here. So alpha, linear means we used L. Okay, this was delta T. This was straight away T based on the temperature. Then the second one, delta T we had used now. Let's make a correction. Delta T, change in the temperature. This is delta V upon V will be again delta T. Only difference here is it is for area, sorry, and for volume it will be delta V upon V. This we had seen for volume. For area we have to use the letter A. Here also for volume you have to use the letter V. We can also write L, we could take this side and write it as alpha L delta T into L. This is like a subscript, not a letter, just to indicate this is for linear expansion. Into A. This will be, just we take it up. So these are the three equations for the thermal expansion. That is, first one is for linear, second one is for area, and the third one is for the volume. This was called as the coefficient of linear expansion. This is coefficient of area expansion, and this is coefficient of volume expansion. Coefficient of linear expansion, this is area and this is for volume. I told you for these things, this is constant. This remains constant. It is not dependent on the temperature. But for volume, this fellow depends on temperature. It depends on the temperature. This is constant, but here, especially for gases, if the thermometer has a gas, then definitely, okay, same. There is more this. Whenever this is expanding, okay, especially for gases, you can write. I had given all this in the previous class. Now it's something we are going to derive based on this. That's why I'm just explaining of the previous one in short. So we'll find what is the coefficient of volume for an ideal gas. Coefficient of volume, this alpha V we are calculating for a gas. I had given you all at the starting of the chapter, there's something ideal gas equation. This is the ideal gas equation which we have already seen. PV is equals to mu R T. All this was given. P is the pressure, V is the volume. Okay. Then mu was in terms of moles, R was the gas constant, and T was the temperature. No need to write again. Just have to know the equation. Now what we are going to do? We are going to take pressure constant. We will not change the pressure. We can add constant pressure. You can. So pressure is constant, so it will not change. This is also constant, pure value. This also has a value. This is also constant. So only what can change is the volume and the temperature. As the temperature changes, your volume will change. Means if you are increasing the temperature, the gas will expand. This is constant, pressure is constant, so change in the volume. If you change the temperature, volume will change. Okay. Now we know that for volume expansion, we know this formula just now we had written under the block for volume expansion. We know this delta V upon V is nothing but alpha V into delta T. Just now we had seen. Under the diagram I had given you all this. So we know V, we could take that side. Delta V is nothing but alpha V. I just brought it up. Same thing. Here I had written under the diagram. So we'll put it as 1. This will put it as 2. So put value of delta V from equation 2 in equation 1. Delta V will put here. Put the value of delta V from equation 2 in equation 1. So what is this value? This will come here. So what is going to cancel? Delta T will cancel on both the sides. Instead of delta V, I put this. I just write this together. P V alpha V is equals to mu R. We know that what is PV starting only from the ideal gas equation. This is mu RT. PV value is mu RT. First line only we have written. So just put this. Instead of PV, you can write it as mu RT. What is PV value? Mu RT. So mu R. This will cancel. So this is 1. So alpha V is 1 by T for ideal gas. It is dependent on the temperature. If you want to know what is the coefficient for an ideal gas under constant pressure, it is 1 by T. T is the temperature. This is coefficient of volume expansion. Next, we will see what is the relation between coefficient of linear expansion and coefficient of volume expansion. In shortcut, if you want to write relation between what is the relation between alpha L and alpha V? What is the relation between alpha N and alpha V? This is, coefficient of linear expansion, and alpha V is coefficient of volume expansion. We have to find a relation between them. We know that volume is L cube, or V is L cube. If you know the length and this of a cube, okay, volume is nothing but length into length into length. So that is L cube. For linear expansion, we know that this formula I have given you under the diagram. Alpha L it's nothing but delta L upon L is equals to alpha L into delta T. So I have just taken that L up. for volume expansion. Change in volume is nothing but delta V will be nothing but original of final volume expanded volume minus original volume. With the help of diagram I'll show. Suppose if this is the volume and it has extended, suppose after heating it became slightly bigger. So how much is this shaded region is nothing but how much it has expanded, the final expanded volume minus your original volume. Change delta V is nothing but the bigger one minus the inside one, so that will get the change. Okay, so what is the expanded volume? Obviously it will be how much it must have extended. Length must have increases by delta L. If this was the original length, so that must have L plus delta L. That must be the final volume. And original volume was what? L cube. After heating, every length must have increased by delta L. Okay, there will be some extended one. So that is the expanded volume, and this is your original volume. So we'll use A plus B the whole cube formula. L cube plus 3AB square or A square B plus 3AB square plus AB cube, and then that is minus L cube. A square plus 3A square B plus 3AB square plus B cube minus this is your L cube already there. I've used A plus B the whole cube formula. Now this delta L is like a very small value. Okay, it will change by very small fraction. Suppose 0.01 length has increased. Obviously whenever some expansion is there, it will not extend by some 1 meter, 2 meters or something. It might extend by centimeters or millimeters also. Okay, not going to be such a high expansion. So whenever it's a small number already, you're squaring it, means again it will become more small. When you're cubing it, it will even become smaller. So what happens is these quantities delta L square and delta L cube are very very small, therefore can be neglected. And this will cancel. So this two if you neglect, what will be left is 3L square delta L. So this term and this term I am neglecting, so only this will be remain. Now put the value of delta L and put this as what is delta L value and put it here. Two substitutions I will do here. One is put delta L value here, 3L square alpha L delta T. Okay, you can put this as 1 or equation 2 and put it here. 1, put value of Before this, put value of delta L from 1 in equation 2. This delta L I put here. But now the answer what I want is in terms of relation between delta V. So right now it is only alpha L. So I want something in terms of volume. Okay. So what is this? L into L will L square into L will give me L cube. Alpha L delta T. And what is L cube? Volume. So we'll just put it as volume. L square into L I got as L cube. So put it as delta T. Just bring this or just put the value of delta V. What is delta V for volume expansion? We know that volume expansion, we know delta V is nothing but alpha V into delta T. Just put it here. So what all is going to cancel? Delta T, V and V. So alpha V is 3 times alpha L. So this is the relation. Alpha V is 3 times alpha L. We have to derive the relation between alpha V and alpha L. This is the same way. Next we will derive the relation between area and linear. This was linear and volume. So next will be linear and area. Linear expansion and coefficient of, right here only the bracket alpha L and coefficient of area expansion. On the textbook they have given for a rectangle, so we'll assume it to be a rectangle only and solve. We are doing it for a rectangle. So just draw the diagram. Suppose if we had a rectangle, suppose only this part I will draw, one side only. Suppose this is the extended part. This is suppose your length. Consider it to be A and breadth to be B. What will be this area? A into B, length into breadth. Now suppose if this has increased by small distance delta A and breadth has increased by small distance delta B. What will be area of this strip from here to here? This strip is, what is the length? Length into breadth. So this area will be, I'll consider it as delta A1, change in the area. How much it will be? Length is A and breadth is delta B. Same way this area will see, what is A2? Change in area. This. So what is this one's length? This one's length would be delta A and this would be breadth. Or B into delta A, whichever way. Either you write this first or that. And this is how much? This third small area, this piece, delta A3 I can write. This one's length is delta A and breadth is delta B. So just write, consider rectangle it of length A and breadth B. When temperature changes, area expands. Therefore, increase in the area will be how much? This will increase. So we are calculating how much it has increased. Increase in the area will be total delta A change. Total, how much it is. So delta A1 plus delta, this area plus this area plus this area. Change, increase in area or change in area, whichever. How much is it? Delta A1 is nothing but here A delta B. A2 is what? B delta A plus delta A delta B. Okay. Now, next step. We are just in that what is delta L was nothing but alpha L time. This is increase in the length. Okay. Alpha L, this way it was into delta T. Then normally we take L up, alpha L into delta T. So using the same formula, this is length. So instead of now length, what we are using for length A. So this will become A then. And for breadth, it will become B. So same thing. So what will be delta B now? Same thing I will use alpha L. This is for linear expansion. So I'll keep L only because coefficient will not change. L only. Only thing, length is A now. Or this was for B, no? So this will be B. Delta A will be alpha L A delta T. Just I'm replacing this by A then. So this will become A. If I'm replacing this by B, this will become the same thing. This L we don't have to change because this means linear and this means length. Okay, this L means length and this means for linear. So that L we have to keep same because these are linear expansions. Length is increasing. Even breadth goes under length only. And the third part, delta A is nothing but again same thing. This will become AB alpha L delta T, then again AB alpha L. No. Alpha L into alpha L will give me alpha L square AB delta T square. Multiplication, this is alpha L into alpha L will give me alpha L square A into B and this will be T. Now these two terms are same. So this will be 2 times AB okay. What all is common here now? AB is common, alpha L is common and delta T is common. So what remains inside is 2 and 1 alpha is L will remain because 1 alpha is gone out and 1 delta T is left. So now over here this value is very small compared with 2 because this will be something 0.00001 or something like that, very small change, and 2 is a big number comparatively. So if you are adding extremely small number to this 2, it will won't make any much difference. It's very small compared to 2 compared to 2, so can be neglected. That's why this part we can neglect. So 2 AB alpha L delta T. And what is A into B? A into B is nothing but your area. Length into breadth, no, is nothing but the area of your rectangle. In the final step, what is your delta A formula? Actual for area expansion, delta A is nothing but alpha A just put it here. This will cancel, this will cancel. A and A will cancel. Therefore, alpha A will be equals to 2 times. So this is the relation between area and coefficient of linear expansion. Okay. So the two relations are this, you have to know. Alpha L is 2 times this, alpha is 2 times alpha L, and alpha V is 3 times. So these are the two relations which you have to remember. There's normally a question, what happens by preventing thermal expansion of a rod by fixing its end rigidly. Means what? Suppose there's a rod, okay, which is fixed towards the end, and some heat is supplied for this. Okay, now this, there is some heat which is provided for the rod. Under normal conditions, what this should happen? Whenever lot of heat is provided, this rod should expand. But now we are not allowing the rod to expand. We are fixing it by some rigidly, means like some substance which is not allowing it to expand. It's fixed at both the ends. Now what will happen to this rod? We are preventing means we are not allowing thermal expansion. What is going to happen is, as thermal expansion is prevented, what is going to happen? There will be a lot of, like, it wants to expand but is not able to expand. So what happens is, there's a something called a strain which develops inside it. Okay, like there's some force which is up this. So the rod acquires means gains a compressive strain. Why? Because what is happening now, this rod wants to expand, but this supports, these are your supports, the supports is trying to stop it from expanding. So there's a external force which has been expand this on the rod back. So due to the external force from the rigid support, these are rigid supports at the end, at both ends. This stress, stress is nothing but like the force acting on that particular area of the rod. This stress set up in the rod is called thermal stress, because it is not able to expand itself. So there's a lot of stress developed inside the rod. This stress will damage the rod or will cause bending of the rod. Either the rod will bend or the whichever the side, okay, whichever are this, if they are weak enough, then they will bend or this rod will bend. The stress will cause bending of the rod or I can write that much only. This stress will cause bending of the rod and can damage it. Because there's like a lot of force which is created on it, and that's why it will bend the rod. In terms of on the textbook they have given in terms of values also, not needed, only this much is enough. Next is specific heat capacity. I'll just tell you what is first heat capacity. What is heat capacity? In the sun, suppose if you keep a steel plate outside, okay, and if you keep a wooden plate, okay, in the sun, if you are keeping a steel plate and a wooden plate, obviously you know that this steel plate will become hot faster. So there's a sun, okay, this will get heated faster. Okay, whereas this comparatively will take some time compared to the steel. Why is it so? Is because heat capacity of steel is low compared to wood. Takes time to get heated. So what is going to happen? Now this steel plate has very less heat capacity. It cannot keep inside whatever sun heat it is getting. No, it has to store inside it. Now this has very small capacity. Same like how you have. I have very less capacity to eat. So what happens if you eat very little, you will feel full. Okay, your stomach can, or maybe it take very little food. Some can take lot of food. So it's because it depends on their capacity. So the same thing, every object will have its own heat capacity, how much of heat it can take. So now the moment it takes very less heat, it is full now. So what happens? It will start radiating back all this heat. So that's why when you touch it, you will feel it very hot because it is giving out that heat. Okay, so heat capacity of steel is low compared to wood. Now the same thing, suppose if you take So this is normal. So I'm trying to tell you difference between what is called as heat capacity and specific heat capacity. Don't write as of now because I'll give you the definition. Specific heat capacity. If I have a block of suppose 1 kg, and if I have a block of 10 kg, yeah, before that also if I consider, okay, heat capacity of 1 kg, suppose wood or steel or any object, suppose consider steel only and steel only, and you keep it under the sun. You keep 1 kg block of steel and 10 kg block of steel in the sun. So obviously you know that this will get heated faster. Okay. So what you say, heat capacity is less. Here what is happening? It will take time. The heat capacity is more. Why? Because overall by the time the whole 10 kg block gets heated, it will take more time. So this bigger the block, more the mass, more time it will take to get heated. Now, what is the difference between this now heat and specific? Specific deals with per kg, per kg block. So here specific heat is, just a second, so much of disturbance. Specific heat is nothing but heat capacity per unit mass. It's per unit mass, or per unit, like per kg, how much time it will take. Here maybe like you will need 1 joule, suppose. Here you might need 10 joules. Heat to heat up this full block, you might need suppose 1 joule. And now for 10 kg you might need 10 joules. But for specific heat capacity, it talks about how much you need per kg. So whether it is a 1 kg block, 10 kg block or 100 kg block, it doesn't matter. Specific heat talks in terms of per unit mass or per unit kg. So here under this also, this whole block will need 1 joule. So this it's like 10 parts. So here also for 10 kg, what is specific heat capacity? I want to know how much it will take to heat up its 1 kg mass, one small piece. So that also will remain as 1 joule only. It's like 1 joule, 1 joule, 1 joule. Here also like there will be 100 parts. This would be 1 joule, so 100 pieces. So whenever someone asks you what is specific heat capacity of this, so you have to think how much heat you need to heat up its 1 kg of it. So whether it is 1000 kg, 10 kg, 20 kg, you have to talk in terms of per kg. But whenever you have heat capacity, it is overall, like how much it would take to heat up the whole 10 kg block. So that is the difference between heat capacity and specific heat capacity. So just write the notes in terms of definition. Just before that, again I'll explain if you want this. Suppose if you have water or anything, water is at suppose 27 degrees Celsius. Now I want provide some heat. I want to make it 28 degrees Celsius. So obviously some heat I must have to provide to make it from 27 to 28. So how much of heat I need to change it from 27 to 28 is nothing but your heat capacity. Okay. In terms of definition, if you want to increase the temperature of any object by 1 degree Celsius, so that way it will work for another 1 degree, 28 to 29 that way. Okay, so as per standard definition, it's like to increase 1 degree, how much heat I will need. So I'll give you the definition. Heat capacity of a body is defined as the amount of heat required to raise its temperature through 1 degree Celsius or 1 Kelvin. We had seen in the previous class various ways you can represent temperature in terms of degree Celsius, Kelvin, Fahrenheit, like that. So you want to increase by 1 degree or by 1 Kelvin, how much heat you will need it. This is heat capacity of a body. So as per this, delta Q upon delta T. Delta Q is amount of heat supplied and delta T is nothing but change in its temperature. And S is nothing but heat capacity. Okay, heat capacity does not talk about mass, how much kgs you want to heat. Heat capacity talks in terms of general, whether it, so more the block. So what is going to happen if you want to change? Little water is there. Obviously, you can do it faster. But if this whole block is there, this will take more time. So this will have higher and this will have lower heat capacity for this because it depends on the mass now. Like more the mass, more the this. The next topic is specific heat capacity. Right? Specific heat capacity of a body, of material also you can say, is the amount of, is defined as the amount of heat needed required to raise the temperature of 1 kg. Here you underline specifically 1 kg or 1 whatever mass, unit mass, 1 kg of substance through same like heat only, but only here is specifically 1 kg through 1 degree Celsius or 1 Kelvin. So it's like again the same thing. If you have something 1 kg and if you have 20 kg, suppose specific heat is same at both places, because you will here also will talk about how much you will need to heat 1 kg of that. Here also you will need what is 1 kg of that. So we will talk in terms of kgs for specific heat, so it will remain same. So under this block, if I want 1 joule to heat to raise it to 1 temperature, here also I will need 1 joule to heat up this small 1 kg. So the formula will be, use a different letter now, small s. So here this kg per kg is there, that's why s upon m. This is small letter, okay, and this is capital. Per unit mass, per unit kg, that way. 1 by m I'll keep side. What was s? Delta q upon delta t. Where m is the mass, small s. If you want, you can write like this to make a difference. Small s is nothing but specific heat capacity. Rest all is same. This is amount of heat needed, and this is change in the temperature. Same from the previous heat capacity. Extra is only this mass per unit mass. Same way how you can define per unit kg, you can also find out per unit mole. In chemistry must have studied those Avogadro's number, how many particles are there, based on that a small piece like per unit kg, so per unit mole also you can calculate, especially for gases, liquids. So instead of kg, if you are calculating per mole, then it is called as molar capacity. It is defined as the heat, the amount of heat required. Same thing, you just have to change one word. Instead of kg, it will be 1 mole. or 1 Kelvin. It is denoted by C. Specific is denoted by small s, no? So like that, this is denoted by small c. So molar per unit mole. M is for mass, so mu will use for mole. So C is molar specific capacity, that is denoted by C. Sorry for the external disturbance. Not even, this is neighbors. I cannot even say anything to my neighbors. So this is delta S, we know it is already delta change in the temperature, and this is how much of heat you need. Just write both the units and keep. I think I have not given unit of specific heat capacity. It is S, small s. Since we use it as per kg, so joules kg per Kelvin or per degree Celsius. Joules per kg, -1 is per kg per Kelvin. Or in terms of suppose CGS system, if you want to use, you can use in terms of calories. Grams per degree Celsius. This is SI unit. This is CGS system. This is of heat capacity. Unit of molar specific capacity is joule. Instead of kg, only thing it will be moles, rest all will be same. It will be moles. And unit of heat capacity, only heat, starting one, it is capital S. There is no kg, nothing involved, so it is just heat per Kelvin or this per. There is no mass, no molar involved in the heat capacity. It is plain, just heat per change in temperature. Temperature, this is Kelvin, huh? K is for Kelvin. Unit of temperature. Next topic is this is all about now little bit of theory. What is calorimetry. How we have no thermometer like that. So same way, this calorimeter is also an instrument like thermometer. Only thing, this calculates in a isolated place. What happens is, in general, I will just explain. Now I want to calculate someone's what is the heat which is any object which is giving out. If you have a hot object and if you have a cold object kept together, what is going to happen? Some temperature will go, okay, it will fall, go this side. Same thing, suppose if we have here 28 degree, you have here suppose 52 degree. So what is going to happen? It will start giving out, losing out its this heat till they become same. Okay, so always heat gets transferred from higher to the lower, so that it becomes it comes at equilibrium. Now if you want to calculate how much is gone this side, what happens while going from here to here? Not necessary, there's an environment also, no, external environment. If you have kept a hot cup of tea in water for it to cool down, suppose, now is this, now suppose this was like boiling hot water at 100, so is that whole thing going in the water only? This, no. Why? Because some of the heat is gone out also. So based on how much water it has absorbed, this water, how much heat it has absorbed, you cannot calculate from here because some is gone external. So you have to make sure whatever you're calculating is how much heat it is given out. You have to calculate everything based on the external environment also. Okay, but calorimetry can be done under isolated process, provided like if there is no external only, everything is inside a closed packed one. If you are keeping this one object which is at 100 and this is at suppose 20, or we don't know what exactly temperature and we want to measure how much is it, so we will keep everything insulated. Insulation means there is no external air, nothing to take the heat away, everything gets purely transferred from here to here only. The transfer should not go to the external environment, should be within this much only. Then you can get the exact count or exact readings of the heat, how much heat has been transferred. So for that we normally use something, the device called as calometer. This also is nothing but measurement of heat only, and the device used is calorimeter. I'll just show you the diagram of it, how it looks like. I'll just share the slide. Okay, so now suppose that yellow color small dot which is there inside is the sample. Sample is that material you want to calculate how much heat it is giving out. If you first it is heated, okay, to a very high temperature and quickly it is put inside that container, that is this box. What you can see is nothing but a calorimeter. It contains of like it's a metal vessel. Okay, inside that it's an insulated container. All this is insulated. Insulated means like no external air should come in and whatever is inside should not go out. Now I want to check how much is the that yellow object giving out its heat. So what I put at the side, I put water. So now they have put the thermometer inside it. Whatever heat the yellow is giving out, the water is absorbing it. So how much ever the water is absorbing, it will indicate on the thermometer. If the water is getting hot means thermometer, that mercury level will rise. So by how much amount it rises, that will show you how much the yellow body has given out the heat to the water. And in between there is a stirrer in order to stir, so that it doesn't remain at one place. The heat goes towards the thermometer side also. So this is how calorimeter looks like. So what principle it follows is, in isolated system, isolated means no heat transfer takes place, or you can say no heat is lost to the surrounding environment. Isolated means this no heat is lost to the surrounding external environment. When a body at higher temperature is brought in contact with lower temperature, the heat lost by the hot body is equal to the heat gained by the cold body. It means what? There's a hot body and there's a cold body. If this one is losing 2 degrees Celsius, this means this fellow is gaining 2 degrees. This is gained under a isolated system. Means nothing is lost to the environment. Suppose if they are very close to each other and nothing is going out, from one to one only it is going, then if this one is losing 2 degrees means this one is gaining 2 degrees. So under that calorimeter also same thing happens. If that yellow object which I shown in the diagram, that small object is giving out 2 degree means water also will gain 2 degree, and then it will show on the thermometer. So calorimeter is the device used to measure this heat. Consists of metallic vessel and stirrer of same material like copper or aluminum. That outer body is made up of copper or aluminum, and then it is insulated. Vessel is kept inside wooden jacket. Wooden jacket means insulated material. Which contains heat insulating material like glass. Glass is also is a wool, pure this wool. So some kind of insulating material it is filled up with, even wood also, which will not allow any air or external temperature to affect the internal one. The heat lost by the sample is equal to heat gained by water. This heat is indicated on the thermometer. It was like this, no? Something. There was a sample, there was a stirrer, this was closed, and this is a thermometer. So whatever is going here to the water, it will show on the thermometer. So if it is giving out 5 degree, this will show 5 degree rise. And that's how you can calculate how much that heat is there inside the object. Instead of water, you can use any other reference also. Depends on the calorimeter. This is a stirrer. Okay, I'll stop here. Next topic is also interesting, that is change of state, like simple ones, melting point, boiling points, freezing points, that I'll do in the next class. Just go through the previous first recording if you have not gone through. Okay, if you have finished, I can leave.